We are finishing chapter 3, our journey. Our observing and wondering and trying to figure out what's going on. All those topics in quick review, how are they connected? Newton's first law of equilibrium, I call it. Law of balance. Unbalanced force will make you increase speed, decrease speed, or turn. But if you got more mass, Newton's third law. Remember that? And how does it lead to this? How does it all lead to this? Let's just say this and then explore it. What do we know? This is why it was critical to understand mass is not the amount of matter. More matter, more mass. More matter, more inertia. That is, more mass will resist accelerating more. You know acceleration means those three things. Also, though, there's another thing. Not just resisting acceleration, but this weird, strange gravity force, which Newton didn't know how it works, how there's a pull, but he was able to write an equation for it. And here's the key. Where did he get his equation? He looked at Kepler's laws. Remember, Kepler took Brahe's dots, right? Stack of dots. And he figured out how planets move. All of them move according to these three laws of Kepler. But he didn't know why. At that time, Galileo was doing his work too. Newton wasn't born. Newton comes along, gets Galileo's work, creates these laws, and we're going to see how they lead to this. And then he's got to write mathematically laws that give you Kepler's laws of motion for planets. But Newton's laws apply to all things, not just planets. But they apply to planets too, so mathematically it's got to give the same result. Elliptical orbits that increase speed and decrease speed slightly. And very small eccentricity to the orbit, really, too. And so he had this thought, too. Look, let's talk about this. Let's talk about where it came from. I mean, you know the laws. If I look at this, it wasn't moving, and now it speeds up. I didn't throw it. Why does it go faster and faster? Why, when it goes away, does it go slower and slower? Decrease speed, increase speed. Why does that happen? I mean, it's accelerating. You got to blame someone, yet no one's touching it. Right? No one's touching it. Who are you going to blame? How does that work? Maybe this, right? Maybe at 23 during the plague on his family farm, maybe an apple hit him in the head, or he looked around and looked at Earth and looked up there and probably had nice dark skies. So maybe all things, planets, sun, moon, apples, all matter, all objects pull all other objects. In the book, I call that point number 4. Doesn't matter. And maybe objects with more mass pull harder on you. So you walk by someone, they don't pull you to them, but if you fall, Or if I let go of this, it doesn't stick to me like a magnet. It's being pulled harder by the thing with more mass, Earth. If you got more mass, it's going to pull harder. So Earth's got more mass than me, so Earth pulls harder than me. But if you got more mass, you get pulled harder. There's more to grab onto. If I'm pulling on this, put these together, I'm pulling on both of them, and the total is twice as much. How do I do that? Remember, we're letting that go. We're letting it go. That's the brilliance, to be able to let that go. What's the mechanism? You got to get into Einstein's warped space-time to start thinking about that. More mass means you're going to get pulled harder. We'll explore that. You pull harder and you get pulled harder. I'll show you that. And the farther apart two objects are that are pulling on each other, the weaker gravity gets. Two objects are pulled, the farther apart two objects are, the weaker the pull between them. Remember, A pulls B and B pulls A, same strength, remember that? It's an inverse square law. So if you double the distance apart, it gets 2, double the distance, squared. 2 squared is 2 times 2 or 4. Triple it, 1, it's double and triple the distance. It's 3 squared, or 9 times weaker. Inverse, weaker, square of the distance law. And then we get a certain effect called the tidal effect. So let's talk about that and explore it a little bit. But this is it. This is the end of the chapter. So let's take a look down here and see how that all plays out. Don't forget inertia either. So according to this idea, and there is an equation, of course, any two objects pull each other. Now, if you dig into Newton's equation, you find that the pull for most objects is tiny. You need astronomical sized objects to really see. If these were floating in space over a long period of time, they'd come together, as long as they weren't moving past each other, right? So everything pulls on everything else. You'd think you get tired. You realize that you're pulling on everything. You're pulling on sun. You're pulling on... How does that work? Well, Einstein says that your mass warps space-time. We don't have much mass, so we don't warp space-time that much. That's the mechanism. Einstein keeps getting tested, and he keeps passing the test, and he keeps predicting new things like gravity waves. Crazy. We don't need to go there. That's kind of chapter 0. We'll stick with this idea. So this says that all things pull all other things. What else does it say? Objects with more mass pull harder. So if I replace this with something that has more mass, then that's going to pull harder on this one. Right? That's going to pull harder. This doesn't pull as much. Additionally, okay, that's going to pull harder. Wait a minute, check this out. Newton's third law. If A pulls B, then B pulls A. Equal strength, opposite direction. But these are the same mass. What about this? Does that still work? Yeah. If A pulls B, B pulls A with the same strength. Why? Well, A pulls stronger because it's got more muscles. It's got more mass, more stuff to grab. So it's going to pull this stronger. Funny thing is, now B is pulling A. It was pulling this, then I replace it with this, now B's got more to grab onto. It's just a way of thinking, right? We don't know the mechanism, but it's kind of like it's pulling this piece, it's pulling all the pieces. You put more mass, then you're going to get more pull. So, additionally, if you separate them, right, as I said, you separate them further. So I can do measurements and things, but you're not going to measure that pull now with super careful, subtle measurements. Maybe you might be able to get a pull hanging from the thread, do stuff, and that was kind of done. But as I double the distance, the pull gets 2 times 2 or 4 times weaker. Triple the distance, 3 times 3 or 9 times weaker. 10 times the distance, or 10 times 10 and 100 times weaker. Now, why does that make sense? Okay, let's take a look. And why do you need gravitation? Based on those laws. Why do you have to invent the idea of gravity? Well, take a look. Like I said, if there's no gravity, then when there's no forces, then the forces are balanced. There's none. So when I let go, it should do this and just float. But it doesn't. It goes faster and faster. And you look around, who's doing that? Well, the most massive thing around, Earth. Every piece of Earth is pulling a teeny tiny bit from every grain of sand. And the pieces farther away in Argentina, Australia, South Africa, wherever, anywhere, all those far, they pull weaker. But all those pulls from every piece of land, of water, even air, all pull and they give that. In this Newtonian way of thinking, right? Leaving away warp space-time a bit. So somehow it all comes together as a pull. Let's take a look here. See, you have to invent the pull of gravity. Let me do a little go a little Galileo on you. Drop some bowling balls. Let's here you can clearly see which one's going to have more mass, and here's even clearer. So take a couple things, and you can feel them. Which one's getting pulled down more? The one you have to push up harder on. What does that mean? It's got more mass. It may be smaller, but it's still got more mass. I mean, this is bigger, but this has still got more mass. I can feel it's getting pulled down more because I have to push up harder on that than I do this. If I drop any two objects and I get their bottoms lined up and I drop them, I let them go. What's the result? What happens? You think it in your head, you might get it wrong, like so many people got it wrong in the past. This is, again, this logic is challenging, but it's hopefully fun. Which one gets pulled down harder? The one with mass, right? It's got, Earth can grab onto it more. That's just a way of thinking of it. So that's gravity. This one gets a stronger pull down. Right? You attach a spring, it'll stretch more. This one won't. But wait a minute. This one's getting pulled more, but it has more because it has more mass, right? But what else does it have because it has more mass? More inertia, more resistance. So if you have twice as much mass, you get pulled twice as strong, but you resist twice as much. That's it. That's why defining mass correctly is important. This one will get pulled twice as strong by Earth, but it will resist twice as much, and they will do it. Do it. 10 times the mass, whatever, 5 times. And you gotta do it. You gotta repeat it so you make sure that you're doing it. But this is a big difference. You would see a big difference if there was a big difference. Now, it's true if you drop a piece of paper or a cotton ball, the air is going to affect it. So you've got to rule that out. You can do it in a vacuum. Just don't be in the vacuum or you'll explode. But right? So that's, oh man. So it is accelerating. There must be a force. There must be a force. Oh, make up a force. Okay. This one's got more matter, so it has more mass. What do you mean more mass? Oh, it resists more, but it gets pulled stronger. Right? This one resists less. It's easier to accelerate it than this one. But it's pulled less. Pull stronger, resist more. Pull weaker, resist less. Together. If you understand that, wow, you got these laws. Pretty cool. So it doesn't depend on the mass. And Kepler even realized that in his laws. But he didn't know, he just didn't have this all sorted out yet. He didn't quite get to chapter 3. Well, he got to chapter 3. He didn't get to the end of chapter 3. All right, or chapter 4. So let's take a look here with astronomy. Right? Remember, I mean, well, we don't need to do that. Okay, and then we're going to have a cool thing, an extra cool thing that's going to it's showing up here at the end of chapter 3, and it's going to show up at the end of chapter 4. Check this out. Review everything. When it clicks, when you've got it all, but you know, you got to check yourself because you might get it wrong. Is Earth accelerating? How do you know? Well, it's turning, certainly. Let alone that subtle increased speed, decreased speed, it's turning. What's causing it to turn? There's none of this in space, right? So and Kepler told us, and Galileo saw Venus and saw Jupiter, and it's like, yes, it's heliocentric. Planets, they always sell these things, kind of bug me a little bit. They're not the right color, really, and I mean, sort of, but no. And they're not the right sizes in comparison, but, you know, I guess they make you wonder. But there are all these planets, I could set it up. Well, they're pulling on everything's pulling, right? Just some of it's tiny, like you and me. You walk past someone and go, oh, you pulled me. So we don't notice this. Magnets are stronger. You can really see that even on a small thing. Okay, so again, what's pulling on Earth? Not gravity. Gravity is not an object. What object is pulling on Earth? Well, we blame it on sun, right? How does that happen? Well, there's a big stretchy rubber band. No. There's a rod. No. How does it happen? Ask Newton. I don't make hypotheses, he says. I don't know. I just know that it's accelerating, and that requires a force. Just like when you drop something, it accelerates, and that requires a force. So let me write a math force that has a strength that will give me Kepler's laws. Check this out now. Right? Here we go. Earth is orbiting. It's accelerating because it's turning. Who's causing it? Sun. Sun's pulling on Earth, we say, with a gravitational force. If sun's pulling on Earth, then what? Earth is pulling on sun. Remember that? Who's pulling stronger? Same. Why? Sun has more mass, so all that mass pulls stronger, and it's pulling on Earth. Now Earth has a lot less mass, but it's got more to grab onto. So nonetheless, they pull equally on each other. Who gets affected more? Equal force, less mass, less inertia. That was gravity. This is the inertia makes this easier to turn, so it swings around like that. Same with moon, right? So now we get another cool little effect. And Mars is out. Mars is out about, if this is 1 AU and this model is not right, then Mars is at its closest over here is another half an AU out here. It's closer, so stronger, but then Mars has less mass. So, you can calculate all that. In fact, all the planets are going around pulling on each other. We'll see that comes up a little bit when we talk about Neptune. But they pull on each other a little bit. I mean, they're pretty far away, but they're enough. So this pull is gas. Everything kind of tends to come together. And as that pull, it's got time, right? Who cares? 1 million years, 100 million years, 500 million years, right? Which is 500 million years. Pulls together. When it pulls together from all sides, solid stuff settles into spheres. Interesting. This force of gravity really is a huge player, and that's it. But there's this one other thing that happens. It's still gravity, but there's an effect. Because what happens as objects get farther away, what happens to the force? The same thing as this, right? You can, what happens to how bright that bulb looks to my eye? It's going to be really bright. I got my eyes closed. If I get twice as far away, it's going to appear 2 squared or 4 times weaker. 3 times farther away, 3 squared or 9 times dimmer. 10 times farther away, 10 squared or 100 times dimmer. It does, right, in terms of capturing the light. Why? Because it's spreading out. Blow up a balloon, the walls get thinner and thinner. It's spreading out. Sound, go farther and farther away. Double the distance away, 4 times weaker, softer. Triple it, 3 times 3, 9 times weaker. So that's light spreading out, a rubber balloon spreading out, sound spreading out. What's gravity? I make no hypotheses, says Newton, right? Warped space-time, which corrects it. It's a little bit different than this. In fact, in here, Mercury feels a very strong gravity, and in there, you start noticing that Newton's just a little bit off. And Einstein grabbed that. Now, check this out, though. One last little bit. Yeah, Earth orbits Sun because Sun is pulling on it. Earth pulls on Sun, but it's got so much mass, that tug is not gonna be much here, but it's gonna be a lot here, same strength force. But Sun pulls on every piece of Earth. This side of Earth is closer. This side of Earth is farther from Sun. What happens because of that? Sun pulls stronger on the near side, the closer side, and weaker on the far side. Sun pulls stronger. Gravity is stronger on anything. So if I take 2 objects actually shaped like this, say me, whatever, I'm going to pull stronger on that side than I am on that side. Why? That side's farther away, and it says, well, gravity gets weaker with distance. That's all the tidal effect is. I mean, you can do the math and stuff, whatever. But what happens because of that? I mean, check out Moon. What side does Moon pull stronger on? Well, the side that's closer, because gravity is stronger if it's closer. Moon pulls stronger on Earth's near side than it does on its far side. Weaker on the far side, stronger, and that's all you have to tell me to explain the tidal effect. What happens? Well, Earth has oceans, so we get oceans, and this affects the oceans as Moon goes around. But Earth is pulling on Moon. Same strength. Who gets affected more? The one with less mass, right? But Earth pulls stronger on the near side and weaker on the far side. What effect does that have on Moon? That's the end of chapter 4, and I think it's really fun and cool. So that's it. It's kind of a simple consequence over here. This is a big player in the universe. Why does it happen? It's not obvious or easy. Just know that was kind of figured out. This is the reason things, as you throw them up in the air and they go slower and slower and then go faster and faster. This is the reason objects orbit sun. If Earth stopped, it would fall into sun. If Moon stopped, it would fall right into Earth. Right? If someone's walking past you and you pull their arm, they'll spin around. If they're just standing there, you pull their arm, they'll go like that. How did they get that way, all that spinning? Chapter 7. Yes. So it's still universal gravitation, but this little effect is that the gravity pull on the closer side, what do we call the closer side? The near side of anything is what? Stronger than the gravity pull on the far side. Oops, on the farther side, called the what? The far side. That's kind of easy, right? Far side, it's farther away. That's why. Why? Because gravity gets weaker with distance. I think we've done it, folks. Use the exercises in the book and so on. And I'll just say section 3.9. I don't test on that, but I think it's pretty cool. And I mean, I tried to keep it as short as possible. But we're talking here, right, late 1600s. He kind of got this when he was 23, and then the laws were published. So his, publishing, I don't know, 40 years old, so whatever. Then you realize that there are laws that work here, and a force between things without touching, but it worked. You tested it. It's like, that's crazy. That's witchcraft. That's nuts, but it works. It gives you Kepler's laws. It predicted comets when they come back. It works. And how do I tell? I tested. Oh, I got the scientific method. Let me test. I would keep testing. Why is one thing hot and another thing's not hot? What is light? Test. What is magnetism? Right? What's that electric force? Electra means amber, that tree sap that's dried. You rub something with that tree sap with fur, and you get like a static electric thing. And like, what's that? They started exploring. What if you mix things? What's going on? They didn't know about atoms yet, but they wondered about why do you mix this and that and this? You get this and then you heat it, and then you do with this different things in the experiments. You write down your results and you keep doing it. You pass it on. You get students to get them to do it. 1800s come along. What is that electric force? What happens? How come when I rub things, they pull? I can hold them. This is a much stronger force. I can't suspend two things and see their gravity force between them. It's too weak. Gravity's weak. But this electric force, I can rub things like a balloon, or I don't know if they have balloons back then, probably not, right? So whatever, you rub things and they pull together, or they push apart. Like a magnet pulls and pushes apart, but it's different. But you keep doing experiments and you find ways of running electric current through wires. And you do all these experiments in the 1800s, and then you realize that when you run current through a wire, it can make your compass move. And so there's some magnetism that's related. And then you put these equations and everything together in a mathematical form. These are called Maxwell's equations. Faraday, Ampere, a lot of folks, Volta, deserve a lot of credit working all this out. And eventually, near the end of the 1800s, Maxwell summarized these equations, or all that phenomena in mathematics. So it wasn't just fuzzy like, yeah, it kind of does this. No, exactly how strong. What makes it strong, what makes it weak. And you put these equations together and you mix them with one little quick little move, and you get the equation of a wave that travels at the speed of light. So light. We started to understand what light was. And then you get to 1900 and you get Einstein's special and general relativity, quantum mechanics, all this stuff. Not that long. You saw how long the course was from Aristotle, right? And get to know some of that history and all. Once you employ this, our knowledge took off, right? Just took off. I mean, it was like 1995 computers, like, the image is loading. Look, you can almost see the image. Now, your pocket, you got this stuff. What's it gonna do? What will we know? So, why? Because of the scientific revolution. It saves lives. You can have kidney transplants, heart transplants, you can do different things. We'll see where stem cell goes, etc. All this crazy stuff that changes our lives. And hopefully we become better people and use our power and our tools more wisely. And we look out for folks that are using it for power, using it for money. There's always those folks, and they will find a way, right, to get your vote, to get up to the top, and then maybe not need your vote. So history is repeating, and it has repeated, and it just repeats. So there's a lot of power here. But when people realize that it wasn't about my opinion, science doesn't care about your opinion. Science is about finding out what's true. And so too, you can challenge authority. And you can create a political structure where you can challenge your leaders. And so that gets woven into our Constitution. These ideas are profound on many levels. I hope you enjoyed them. And in chapter 4, we're going to see why we see what we see, imagining what it'll look like from space and drawing pictures. Okay, ciao, review, just review. It's a lot at first, it gets less and less. Quick reviews, daily, and you've got it. That's it.